Okay, first thing I want to do is look at the packet. If you would look at that, please, the first page of this. Now, we've got these tables of data. One of the things we need to do over the next 6, 7 weeks, whatever that we have left, leading up to our finals and so forth, is begin tying in some of these things that we do. So we'll have a lot of days where it's some partial new stuff, but it's partially going over packets. I just printed off your next full packet that you have to do. Some of you, if you like green.
Oh, yeah. I like green.
Yeah.
That's fun.
I only have a handful of green ones. So yeah. And there's even a couple of orange ones at the bottom.
Wow.
So somebody stuck some colored paper in the copier, I guess. But anyway, so we'll be working on those things, a lot as we go along and tying in the new stuff. And one of the things you see here is this idea of tables of data to be able to work those problems. Every AP test since I've been doing it, I think, has had in the 6 free response questions, one of the problems is a table of data. And usually, not always, but usually it has context to it like this, okay, with units and so forth. And so I want to talk about this just a little bit. I want to focus on part B, because part C and D, they just give you an equation for the temperature, then you work with that, which, is a pretty typical type problem. But I want to talk about the one here where it asks us to work with the table. Now, they say that they want us to evaluate this integral. Now, if you look carefully, that says y prime. Okay, the integral y prime 10 to 25, and use the data in the table. Of course, the data in the table is y. Okay, so what did you think of doing here? How'd you do this? Subtract those?
Yeah.
Now, why would you do that?
That's like the change between that, like in that interval.
Wait, yeah, isn't that fundamental theorem part 2? I mean, right? Fundamental theorem part 2. I mean, forget the table for a second. If I just threw at you an integral of y prime from 10 to 25, fundamental theorem part 2 would say do the antiderivative. The antiderivative of y prime is y, and do it from, and then do f of b minus f of a, basically, right? So you do y of 25 minus y of 10. Now, normally when you have a table of data, you don't think about fundamental theorem part 2, right? Because fundamental theorem part 2 means the antiderivative, which you usually equate with an equation of some kind. But in this case, since they gave you y prime, that's that. Now, this brings up a really important idea. And Richard even said it a little bit. It's the amount that it changed, right? It's the amount that y changed. Because if you think of y of 25, which is 226, and you think y of 10, which is 338, you subtract those, you get negative 112. Now, what are the units on it? Just degrees Fahrenheit, right? It's not degrees per minute, because it's just y, right? I mean, y of 25, this is just degrees minus degrees, right? So this is just degrees Fahrenheit. Now, what's it mean? Yeah, the temperature of the pie went down 112 degrees from 10 minutes to 25 minutes. During those 15 minutes after it had been taken out, starting 10 minutes after it had been taken out, up to 25 minutes after it had been taken out, that's how much the temperature of the pie went down, right? I mean, you need all that in there. You need to mention the 10 and the 25, okay, and you need to mention this change in temperature. It's the total change, or the net change. In this case, the net change in temperature. In this case, net and total are the same. Now, that's actually a very important idea. If you do the integral of a rate of change, because that's another thing that we've talked a lot about, is rate of change. Okay, rate of change is like your f prime. If you do the antiderivative of rate of change, or excuse me, the integral of rate of change, it gives you the amount of change. And the term when you start using a lot is accumulated, the accumulated amount of change. So what we have here in this integral they were asking us for is rate of change. We do the integral of that, it gives us the amount of change. And that's what we have, 112 degrees worth of change of temperature. Now, think about what the units are. What are the units on y prime here? What are the units on y prime? Degrees per minute. And what are the units on dt? Remember how we talked about how that's like your delta x, that's like the width? That has units, right? When we get into these problems with units and we start doing integrals, you really want to think of it this way. What's degrees per minute times minutes? Degrees. So it makes sense that our final answer is in degrees, right? Makes sense. All right, now let's go to the next page because that brings up another scenario that you run into in these problems. Here we have a population table. Okay, so many years during this 10-year period, this was the population of this town. All right, and they want us, from the data in the table, to approximate the average population. Now, I want you to think of some very specific things when you hear the word average in this class. Now, tell me what you guys thought about doing here. Anybody want? I think I gave you a hint on the board that day, but it depends how soon you get done with the quiz, how much time you spent on it. But you remember?
The 10 plus the 0 divided by 2, like the average.
See, that's what I want us to not think of. But I'm glad you said that because that's almost always what we think of, right? So he looked at the population at this time, the population that time, and I'm up divided by 2, or you know, that's kind of like a physics kind of thing in some cases, like a final versus a final plus, you know, average. Of course, that only holds if you have a constant change throughout here. Okay? Anybody else have an idea?
The average value function.
Yeah, what I'd like for us to think about is the average value. Now what somebody in the other class said is they said, well, I just took, since it does say something about left sums, and so if you have that on your brain, thinking of left sums, you think, well, I'll just take these first 5. I won't take the last one because that's what we do with the left, right? And I'll just take and add up these, and then divide by 5 because there's 5 of them. Or actually the person in the other class said, I'll take these off, times them by 2 because they're over 2-year periods, and then divide by 10 because it's a 10-year period, which essentially is the same thing, right? Divide by 5. Okay? And that actually comes out with the right answer here. But that's thinking of it, again, more as an average and not really about what I would like you to think of, which is this idea of what Tim said is the average value. What I want you, there are 2 main times you're going to hear the word average in this class from here on out. And neither time do I want you to think about what we normally think about with an average, which is add them up and divide by how many there are. We don't want to do that. One of them is average rate of change. When you hear average rate of change, what do you do? Slope between 2 points, right? If they want the average rate of change from 1 to 3, then you take the y value at 1, the y value at 3, you subtract them, and then you do a slope calculation. Okay, so when you hear average rate of change, you should then do a slope between 2 points. When you hear average of a function, like that's what this is, average population is the average of the y function, then I want you to think integral, in this case 0 to 10, of the y function divided by b minus a, which in this case is 10 by 0. I want you to think of that. Average. Those are the 2 times you're mostly going to hear the word average from here on out the rest of the year. Average rate of change, slope between 2 points, average value of the function. And I want you to think of this. Now look down at part D. Look at part D on your paper. That's where they get that 1/10 out in front. That's just another way of doing it, dividing by 10. Is put a 1/10 out in front. So on your meaning for part D, what does this integral mean? You should have written it's the average population. It's the average population over those 10 years. Okay? Because what that integral that they gave you down there on part D is the average value of the function. Okay? That's what that 1/10 is. It's not a width. Remember, we don't put the width in an integral. That's the dt part, right? That 1/10 out there is just the divide by 10 part, like what I wrote there. Okay? So when they said find the average population, I should write this integral right here. Now, notice I wasn't even thinking about left sums. Why not? Well, because a left sum is to approximate an integral. So I can't do a left sum until I have an integral written. Now, for this one, it was pretty easy. Like what most of you did, you added them up and divided by 5 or whatever. That was fine. You were thinking it through, and that's okay. But what we're going to get into when we get into Chapter 7 is our integrals are going to be more difficult than this. We may use a table of data, but it'll only be one piece of the integral. And before we can do a left sum, we've got to write out the integral. So I want you to get in that habit. When you see, hey, do a left sum, find the population, well, you don't do a left sum to do the population. You do the left sum to do the integral. You set up the integral so it does the population. All right. Now we do our left sum. So tell me what L5 would be in this case. Tell me what I would write to write it out. Because it says show your computations. 2 times, or I could put f of 0. You'd be perfectly fine to write 2,500. That'd be fine. Okay, you don't have to do the f notation. And then 2 times f of 2. Yeah. 2 times f of 4, 2 times f of 6, 2 times f of 8, and that should be your last one, right? Because it's a left, so you don't do f of 10. Which would be 2 times 2,500, 2 times 2912, 2 times this, 2 times this. Okay, that's going to be the top, and that's like 33,000 something, right? Okay, 33,000. 33,834, right? 33,834 is what you get on top. Okay, and then what do you get on the bottom? 10, right? So you divide it. Now, I want to talk, and so the answer comes out 3,383.4, which makes sense. If you look at those numbers, 3,383 looks like about the average population. Okay, that seems reasonable. Now, of course, that's only an approximation because it's left rectangle, right? And left rectangles may or may not be a very good approximation. So, right, and we'll get into that more today. I want to talk units for a minute. What are the units on this 33,000 number? People times, what are the time here? Years, right? Now think about this. What are the units on what? People, right? What are the units on DT? Years. So this is 33,834 people years. Right? That's what it is. I mean, it's not a very meaningful unit, but there are units like that. Like electricity, do you ever hear of kilowatt hours? There's a Newton seconds. Yeah, Newton seconds, right? There are those kinds of, or Newton meters. Isn't that another one? Isn't that like foot pounds? Have you done that in physics? Like that's something we're actually going to work on in chapter 7. But yeah, that's the units, people use. And then what are the units on the 10? Years, right? And so people years divided by years, you end up with people. So it makes sense that that ends up being average population. It makes sense that ends up being population, okay? Ends up being people. And so I really want you to get in the habit of, when you look at an integral, in a problem where there's units, think about what the units are, because the hardest part of these problems is setting up the right integral. And if you do it thinking about your units, they're not very hard to set up. They're not very hard to set up. Okay, so here's your computations, and here's the final answer, and you can double check that the units are right, and that's what that should look like. All right, I want to show you one problem from 2009. This was the AP test, free response, 2009. This was question number 5. And I want to look at part C. Okay, so everybody read part C. All right, so we're going to do a left sum. How many subdivisions are there going to be? L what? 4. Right? There's 1, 2, 3, 4, 5 points, which always means there's one last subdivision, right? There'd be 4 subdivisions, okay? So it's going to be an L4, and tell me what to write down. Let's do F notation. That's not F notation. Oh, 1, that's my width. You're right. Okay, never mind. You're doing the width first. Gotcha. 1 times F of 2. What do you notice it's different here? Unequal widths, right? Now, we're going to be talking about shortcut ways of writing lefts and rights and midpoints and stuff, but those shortcuts only work if we have equal widths, and 99% of the time we have equal widths. But we said for Riemann sums, sometimes you don't have equal widths. Why in the world would you not have equal widths? If you choose to, you would always have equal widths. We can't choose to, we have no choice. The data is the data, and it's not given to us in equal So this is one of the reasons, a problem like this is one of the reasons I hounded you about write out your rectangle. Write out your rectangle. Height times width, height times width, height times width. Right? You get to a problem like this, it shouldn't be a problem. You guys, sounds like it wasn't a problem. So let's keep going. So the next one is,
It's 3, 7, 5,
and f of 8. And you end up, and you don't use f of 13 because it's a left, so you won't use the last one. And the width, you went this way for the width, which makes sense because if you draw a left rectangle, right, your first left rectangle is at 2, and you go up to 2, and you go over 1. So you'll have a width of 1, and it'll be the output of that one. And then at 3, you'll go up and have to go over to 5. And so you have a width of 2. And so it makes sense that you go that way. If these were rights, you would start here with f of 3, but you go backwards, right, for your width. Because that's what you would do with a right rectangle. You would go up at 3, and then go back to 2. And so it would be 1, 1. Okay? So anyway, you just take those numbers and you add them up and multiply them out and so forth, and you get your answer. So it should be pretty easy. That says show the work that leads to your answer. So that's, again, why I always make you write it, get in the habit of writing this out. Because that's what they want to see. See, this might be a calculated problem here. All right? I don't think it is. I actually think this is no calculated. But still, you need to write that and show it. Okay. So hopefully giving you a lot of examples of different types of problems that we need to be able to deal with here. Okay, now get your notes. Now, I might have put this up early when we were doing chapter 5 and we were talking about rectangles for the first time, but I'm not sure I did. I'm not sure I did. And I think if I did, I told you not to write it down. So I don't think you probably have this written out. But this is a left sum and a right sum. And what have I done different here? Yeah, instead of writing height times width, height times width, height times width, height times width, I just pulled the width out in front. And the width is b minus a over n, right? So instead of writing delta x, I just wrote b minus a over n. So, and then I just have my heights in there, right? I just have the heights in there. So this can be a pretty nice way, because here in chapter 6, we're going to be writing out, we're going to do some on the calculator, we're going to do some where you have to write them out. If it's fewer than 10, we're going to write them out, okay? And so it might be nice to have just kind of a short, quick way to write them out, all right? Now, we couldn't do this on the problem we just did, right? The problem we just did had different widths, and so we pretty much had to write it out the way we did. But if you have equal widths, this can be a pretty slick little way to do it. Okay? Now, you can still write it out, height times width, height times width, height times width. That's fine. And notice the lefts start with the first one and stop short, you know, f of x of n minus 1, and the right start with f of x of 1 and go to x of n. You know, all those things we've already talked about. But we don't have to maybe get this caught up in drawing pictures, and we're not going to write sigmas that much anymore. I mean, there'll be some, you know, obviously on the final and multiple choice in the packets, you'll run into some sigmas every now and then, that kind of stuff. But not very often we have to do that. Okay, so there's a left, there's a right. Okay, next one's a midpoint. Now for midpoint, I just put M1, because the midpoint is halfway between x1 and x2, or x0 and x1. So we'll just call it M1, M2. That means first midpoint, second midpoint, third midpoint, you know, to the last midpoint. But again, we just take the width out. So those three are all Riemann sums. Those are all rectangles. Got the width factored out. Inside the parentheses is the heights. Okay. All right. Now, next one is trapezoid. Now, on the quiz, you guys noticed how I wrote out what I had done there. If you look here. On the quiz, when I wrote out this problem for my trapezoid, notice how I wrote it out. I had the 10 minus 0 over 2, and then the 10. And then I had a bunch of different numbers in there, 2s and so forth. Well, where'd that come from? Well, it came from this idea that in every trapezoid, what do you have? What's a formula of trapezoid? 1/2, b1 plus b2, and then the width, right? So every one has what? 1/2, and the width, right? Every trapezoid, and if we're equal widths, they're all the same. So what I'm going to do is I'm going to actually factor out a 1/2 and the width. Now keep in mind that the width is still, the delta x is still b minus a over n on all these. But the reason the 2 is down here is because of the 1/2, right? I pull out the 1/2 and I pull out the delta x, and that's why I get b minus a over 2n. Now in here, remember how we talked about that? So my first trapezoid, I got the left edge, and then the next, and then the right edge, and then that right edge becomes what? The left edge of the next trapezoid. So that x sub 1, I end up, is the right edge of my first trapezoid, and it's the left edge of my second trapezoid. So I use it twice. And x sub 2, same thing. And x sub 3, same thing. The only ones I don't use twice, the ones on the end. F of x sub 0 and f of x sub n. I wouldn't use those twice. So I only use those once. So when I factor out the width, I factor out the 1/2, I'm left with 1 of the far left edge height, 2 of the next one, 2 of the next one, 2 of the next one, all the way until I have 1 of the last one. So that can be a little quicker way to do a trapezoid. Now, we also talked about another way to do a trapezoid. You guys remember another little shortcut of doing a trapezoid? It involved the left and the right. Here's a left rectangle. Here'd be a right rectangle. Here'd be the trapezoid. Just an average, right? So another way to do a trapezoid is to add your left and your right together and divide by 2. Now, which one do you want to do? I don't care. Which one would be easy? That's the key. If you already have, if I tell you to do an L8, or excuse me, a T8, and that's all I ask you to do, then I think this is probably faster. Like on the quiz, you had to do a T10. Well, I thought this was faster to do. Rather do an L10 and an R10 and an average. But if you've already done L and R, then use up. Okay, so knowing them both could be to your advantage. Okay, like on a quiz, if I ask you for that, I'd take you. All right, now, before we go on, and we got some other stuff to do in our notes here, but before we go on to that, I want to do this right here. I want to do this problem. So you might want to leave yourself some space in your notes and go to another page or something for what we're going to do right here. Okay? So I want to work through this problem. This is similar to problems you're going to have in your homework today. Now today's mostly going to be a no calculator kind of thing, other than adding up. We'll use a calculator. If you got your calculator handy, you want to get it out, not everybody will need it if you forgot to charge it. You will need it tomorrow though, because I am going to pass you a document tomorrow, so you'll need to be charged up, ready to go tomorrow. But we will be doing some adding of some things here on our calculators. All right. So the way that your book's going to write these is going to say I. I means the integral, the exact area. I is going to represent the exact area we're looking for. Now, some of the problems, we could find the exact area with the fundamental theorem. But some of them you won't be able to. That's the whole point of doing approximation, is for ones where you couldn't do fundamental theorem part 2. Right? I mean, that's the whole idea. You can't find the exact area, so you need to do an approximation. But in studying it, we will start with some like this, where we can find the exact area. As a matter of fact, let's do it right now.
It's 1/3
Yeah.
x to
1/3 x cubed, right bracket 0 to 2. Plug a 2 in there, 2 cubed is 8. 8 times a third is 8 thirds. Put in 0 equals 0. 8 thirds. Now let's write that as a decimal. This will be easier to compare. So 2.667 be the exact area to 3 decimal places. 2 and 2/3. All right, and that makes sense because it's you know, if we look at it here, it's a parabola. 0 to 2. And we're looking at this area. Okay. All right. So let's write out an L3. Let's do it using the shortcut stuff we just put in our notes. So tell me what I would write out. Yeah, I'm gonna actually write more than that, but you're right, it'd be 2/3. 2 minus 0 over 3, that's our width, right? B minus A over N. So that's gonna be 2/3 is gonna be our width, okay? And let's do F notation. This would be our F of X right here. So F of 0 plus, no, it would be F of 1. 2/3, right? Our width is 2/3. Plus F of 4/3. Is that it? We stop, right? Because the next one would be 6/3, which is 2, but we don't want to go to the right edge. Plus, what's another reason we know we got to stop? What's another reason we know we got to stop? There's 3 heights. If you have 3 rectangles, there's got to be 3 heights, right? So if you put a 4th one in there, that's no good. You can't have 4 heights if you have 3 rectangles. Okay, so we know we should stop right there. Okay, go ahead and write the next 2. Write R3 and M3. Right, R3 and M3. And then we'll calculate them on our calculators here in a second. All right, if you get done, then you could calculate, like this side of the room do left, this side, you guys over here do left, you guys in the middle do the midpoint one, you guys over here do the right one. That's a lot of people doing right. And remember what you could do here, you could define f of x to be x squared. If you want to put it in as f notation, you can define f of x to be x squared, or you could just, when you put in 0, just 0 squared, and 2/3 squared, and 4/3 squared. I mean, plug in the function, that'd be pretty easy too. And let's get a decimal answer for that. Now I've got the right listed up here, and then what's your first midpoint? 1/3, and then the next one? 1, which would be 3/3, and then 5/3. Okay, so it would look something like this, right? So midpoint's a little trickier. You've got to figure out, okay, this is my width, but the width on all those is 2/3. The width is 2/3 on all of them. Okay. But now let's go ahead and type in your calculator and let's get answers for them. L3, R3, M3. Somebody got L? 1.481. Now, does it make sense that that's quite a bit under the actual area?
Yes.
That's going to be one of our big topics today, is understanding that when we draw a left, is it going to be under, is it going to be over, and what causes it to be under? Well, if you draw a few left rectangles in there, clearly it's under. Okay, and then what'd you get for right? Anybody get right? We got like 15 people over here doing right.
4.148. Yep, that's That's what I got.
Sounds pretty good. Okay, how about the small midpoint group here? 2.593. Now look how much better that is. Now clearly with 3 subdivisions, we don't expect a really good answer. But 3 midpoints isn't bad, right? 3 midpoints isn't bad. We talked about trapezoids is better, clearly, because it's an average of left and right. And again, we're talking about that. Well, if lefts are under and rights are over and you average them, that kind of makes sense. Okay, so we got that. All right, now go ahead and let's do trapezoid. Now, let's do it both ways. Let's write it out the long way first. We realize it would probably be easier to do the shorter way. You got L3 and R3, you just average it. We'll do both of those here in a second. Okay, but let's write it out the long way first. Write it out the shortcut way we just did in our notes. I'm going to have it up here, so don't look if you don't want to see it again. And then put it in your calculator and see what you get. All right, anybody get an answer there?
2.075.
That sounds right.
2.815 for the Formula 1. And then averaging just what we have on the board, I got 2.815.
You'd have to be careful with the averaging one to not round them, right? To take the unrounded values and then average those. But you probably still get close. So 2.815, which is too big, right? Now notice that midpoint was under and a trapezoid was over as an estimate. Now we understand why left was under, we understand why right was over. Midpoint we're not so sure about. Trapezoid, can you tell me why a trapezoid is an over approximation on this?
Well, the curve goes like dips under the triangles a little bit.
So it's because of the curve, right? Because if I was going to do a trapezoid from here to there, right, the trapezoid edge is straight and the curve curves under, right? So the trapezoid, the straight line part of the trapezoid, and I'm going to show a better example of that, is actually going to be over. So it's because of the concavity, right, that causes the trapezoid to be over. Now, is it always true then that a midpoint will be under? If a trapezoid's over, does a midpoint always have to be under? Well, that's a great question. It's not as obvious to tell, and we'll get into that here in a second. I think it is going to have to do with concavity, and we'll get into that here in just a minute as far as the over-under thing. Okay? All right. Now, I want to hold that off here because I have one more of these approximation techniques to talk about. These are the only 4 we've talked about so far: left, right, midpoint, trapezoid. Of course, we did talk about inscribed and circumscribed, which could be a combination of lefts and rights. You don't run into that very much. Sometimes on the AP test a little bit. So, but there we go. Now, obviously, midpoints and trapezoids are better. And we also said we could have taken, to get our T3, to get our T3, we could have taken L3 plus R3 and divided by 2 and average them, and then we would have found it. Okay, now, I've got one more I want to show you here, and this is kind of a strange one. This is called Simpson's rule. Okay, and Simpson's rule says this. Actually, we're going to have two versions of Simpson's rule, so don't write this down just yet. Simpson's rule says this, that if you take two midpoints plus a trapezoid and divide by 3, now the reason we divide by 3 is because we took two midpoints. It's what you call a weighted average. We're doing an average between midpoint and trapezoid, but we're going to actually use midpoint twice. Now, why would we use midpoint twice? Well, it turns out that midpoint is about twice as accurate as trapezoid. Has half as much error, roughly, as trapezoid. So what that means, and here's a little bit of a giveaway, the only way averaging makes a better approximation is if one is a little over and one's a little under, right? If they're both over, the average of you'd still be over, right? I mean, it might be a little better, but it wouldn't be as good as one of them, right? It'd be better than the other. But if you've got one that's over and one that's under, and you average them, you should get a result that's better than either of the other two, right? Okay, so if we've got midpoint that is about half as much error as trapezoid, if we use two of those, that would make the error that, let's say midpoint was under. So if this was under by half as much as this was over, if we do two of those, that means the amount this was under would be pretty close to how much this was over, and if you average them, they should give you a pretty good approximation, right? So that's why we do two of the one that's closer, okay? And then we divide by 3. Now, why do I have this 2 in here? Well, it turns out when we write the formula this way, this is called Simpson's rule. Simpson's rule, okay? Simpson's rule always has to be even. You always have to have an even number subdivision. So you'll notice in your homework, the problem we were just doing, where they wanted to do L3, R3, M3, T3, the next thing they'll ask you to do is an S6, okay? Now, there's a good reason for that, is because if I wanted to do an S6, that would be 2 M3s plus a T3, right? Because the N here would be, if I want to do an S6, that means this would be 6, which means N would be 3. So this N here's a 3, this N here's a 3. Okay, so that's basically all you have to do. I'll never ask you to do an S5. Okay, it'll always be an even number when you're doing Simpson's rule. Okay, so if midpoint is always, if midpoint and trapezoid are always opposite, one's over, one's under. Now I've proven that, and we will here in a minute. But if one's always over, one's always under, then averaging them somehow should be a pretty good idea. And so that's what Simpson's rule basically does. All right, now what would be how would Simpson's rule work? Well, if we were to write out, let me show you what this would look like. If I was to write out Simpson's rule in general, take two midpoints. Well, okay, what was a midpoint? It was B minus A over N. You don't have to write any of this down. Okay, just try to follow me. If midpoint was this, right, we already talked about this, M2, right, all the way to the last midpoint. Okay, and a trapezoid, and I wanted to do 2 of those. Right, I want to do 2 of those. And then I want to add to that a trapezoid, which is f of x0 and 2 f of x1s, right? Oops. 2 f of x1s, da 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 da. Now, if I want to add those all together, okay, we got to think some algebra here real quick. So I want to think some algebra. If I want to add these together, well, before I can add them together, I need to pull out like a common factor here. So how could I do that? Well, let me see. One thing I could do is I could take this 2, not this, but take this 2 and distribute it through there. Everybody okay with that? I can take this 2 and I can distribute it through the rest of these. I'll leave the B minus A out over in there. Okay? So this is going to be 2 of these, right? 2 of all of them. Okay? That was this 2 right here. Okay? And the divide by 3 I'll get in here at the end. Okay? Now, I could almost pull out a B minus A over N, but I'd still have this 1/2 sitting here, right? What I'd rather do is pull out a B minus A over 2N. Is there any way I could get a 2 down here? If I did it, could I multiply this by a 2 on top and a 2 on bottom? Can I do that? What'd I just do? I just multiplied by 1 right there, right? Which didn't affect anything. So I multiplied by 2 on top, 2 on the bottom, okay? Now I want to leave this 2 on the bottom because I want it to look like that. Right? Everybody with me? Okay? So I want it to look like that. And now, this 2 I'm going to go ahead and distribute through there again. So now I got 4 of all these. With me? A little bit? Just say yes. Okay. So now I got this, and I got this right here. Right? So now what I've got is b minus a. Now remember what n is. N is this number right here. Right? This 3. Okay? That's this number. All right. So I've got b minus a over 2n. And now I'm going to pull that out, and now I got everything left. Well, let's see. Where's m1 at? But it's between x0 and x1, right? So I'm going to write these in order. I got x0, I got x1, and m1 is right in between, right? So what would be my first thing? What would be the first thing in here? Be f of x0, right? And what would be the next thing? 4 f of m1, right? And then 2 f of x1, and then it would just keep going like that. 4, 2, 4, 2, right? And what would be the last one before the very end? The very last one would be just f of xn. What would be the last one? It'd be the last midpoint, wouldn't it? Be the last midpoint, which would be 4 mn. But so if I was to work this out, I have this whole thing. Now I got to divide by 3 here, right? I still have to divide by 3. So that's going to change this a little bit, okay? But I'm going to have twice as many of these things. Like here, I'm only going to have 3 of these. If I was doing an M3, if I was doing a T3, I'd have 4 of those, you know, and I add it all together, I end up with 7, which would make sense for the 6. And so I don't want to get all caught up in that. Main thing I wanted you to see with this is the 4, 2, 4, 2, 4 thing. That's what I wanted you to see. Okay? So when all that algebra shakes out, here's what I want you to put in your, go back to the first page of things we were doing. Here's what I want you to put in your notes right here. The long form of Simpson's rule. Okay? Which again isn't that long. If they just ask you to do an S4, that'd be faster than doing an M2 and a T2 and then doing that other formula. It would be at least as fast. Okay, so what do we got? We got b minus a over 3n. Okay, now where'd the 3 come from? Well, that was at divide by 3. And they say, where'd the 2 go? Well, notice we didn't put a 2n on this now when we write this. Notice this just is s sub n. Okay, well, if we're doing the long form, if we're not going to do a midpoint and a trapezoid, we don't have to worry about it, right? If you do an S6, you need an M3 and a T3 to do the other formula, which we'll write down again here in a second. But if you're just going to do an S6, right, you don't worry about it. Okay, so n is just 6. N is just 6 right here. And what we have, notice we have x0, x1, x2. Where'd the m's go? Where are the m's here? Yeah, where the 4s are. The x1 is a midpoint, the x3 is a midpoint. In other words, it's like our width was from x0 to x2 and from x2 to x4. Well, that's why, because when we did the trapezoid, we only needed 3 of them. We do the midpoints, we only do 3. Well, when you do all of them together, it's like having 6 of them. It's like having 6 subintervals. Okay? So if I'm doing an S6, this end here is 6, that's 6, and I should have 7 of these in here. And I screwed this up. I see it already, Richard, why are you raising your hand? I missed. This is not a 2. This is a. Is that what you're missing? Yes. This is a 4. The last one was a 4. So notice it's very similar to the trapezoid. It's got 3n on down here. Now remember, your width is still b minus a over n. Width is always b minus a over n. The 3 is there because of that formula where we divided the 3. You got f of x0, then 4, then 2, then 4, then 2, then 4, then 2. And it always ends with 4s on the ends. And then on the very ends, of course, we only use them one time. And that's because of this trapezoid. All right, now also here in your notes, why don't we go ahead and let's put in that other formula. Now that does need the 2n in it when we do that. That's the 2m sub n plus t sub n all divided by 3. So those two formulas in blue there, those are alternate formulas you can use. All right, if you already know M3 and T3, then you can do S6. Simpson always has to be an even number. Simpson's rule always has to be an even number of subdivisions. Okay? All right. So get that written down, and then let's go finish the other problem we were working on. All right. Let's go back to this problem we were working on now, and let's write out S6. Let's write out the long way. Well, let's just do it together. Okay? So it would be, so tell me what I would write. Now this is S6, so this means N is 6 right here. Right? We have 6 subdivisions. So tell me what to write. 2 minus 0. Down here would be 3 times 6. Right? This n right here is this n right here. Don't confuse it with this formula. That's a different formula. Okay? This n right here is this n. Now that has to be even. Okay? That to do a Simpson's rule, that has to be even right there. Okay? So it's 6. So in it, when I write it out, I should have 3 times 6. Right there. Okay? 2 minus 0 over 3 times n, 3 times n. N is 6. On these other ones, n was 3. All right, then what do I put? Yeah, but in this case, it's f of 0 plus 4. No. Since we're doing 6 subdivisions, what's my delta x on this one? 1/3. Right? 2 minus 0 divided by 6. I'm doing 6 subdivisions, so this is different than all those other ones. The other ones, it was 2/3. We were only doing 3 subdivisions. Here we're doing 6 subdivisions. So it's 1/3. So 4f of 1/3 plus 2f of 2/3, and you keep going with the 4-2 repeating pattern. 4f of 3/3 plus 2f of 4/3 plus 4f of 5/3. How many should we have? No. We have 7. With trapezoids and Simpson, we always have 1 extra. Notice what we had for a T3. 1, 2, 3, 4. Right? For a T3, we had 4 of them inside. For an S6, we should have 7 in here. 1, 2, 3, 4. That's why it'll always end with a 4. Because you always have an odd number in there, because remember, n is always even. Right? For Simpson, we're always doing even numbers. So we'll end up with f of 6/3. We'll end up at the far right edge. Okay, type that in.
Should it be twice as accurate though, since there's twice as many numbers?
You would think it would be really accurate. Yeah. Because there's more subdivisions.
Yeah.
Right. But it's really a combination of 3 trapezoids and 3 midpoints. It ends up with 6 subdivisions because all the midpoint ones are in between the trapezoid ones. So if you have 3 trapezoids this wide, and then your midpoints, cut those in half, right? You can see why you would have twice as many subdivisions. And what do we get? I know it's a lot. And while you're doing that, the other formula for S6 would be to take M2 M3s plus a T3, which we'd already calculated, and divided by 3. And if you do that, you should still get the right answer, a little, or the same answer, a little, these are rounded, so what do you get? You getting exactly the right answer? You should. You should get 2.6 repeat. You should get 8/3. It actually comes out exact. Now, there's a reason why this particular function, Simpson's matches exactly, which we'll talk about later. Since it's a parabola, since it's a quadratic, Simpson's actually finds it exactly. Okay? So it's not a surprise, actually, that it would. Right? 2 Simpsons subdivisions would find it exact, but only because it's a parabola. All right. So that's one new thing with Simpson's rule. Kind of a new way to write, L3s, R3s, stuff like that. So we'll be doing some of that by hand, writing some of that out. All right. Last thing that we want to put in our notes is this idea of over and under approximating. Okay? So if I have a left rectangle, what is going to make left rectangles be over approximations?
When
Well-
it's concave up.
Concave up and on the left side of the rectangle.
Here's concave up and the left is not over. So let me ask again, what is it about a function that's going to make a left rectangle be over if the function is decreased? It doesn't have anything to do with concave, right? Because here's concave up and it's under, and here's concave up and the left is over, right? Concave up doesn't have anything to do with whether a left is over or under. It's the fact if the graph's going up or down, right? So lefts will be over when the graph is decreasing, and when it'll be under when it's increases, right? What about right rectangles?
Opposite.
Got to be the exact opposite, right? A right rectangle will be over when the graph is going up. So increasing versus decreasing. So left and right should be opposite. So if you do a left approximation like the last problem we did and it's under, then a right should be over. And sure enough, that's what we saw happen. Now, they were over and under by quite a bit. The left, 3 lefts was way under, and 3 rights was way over. But we only did 3 of them, so we'd expect it to not be very good. Now let's talk about trapezoids. That was the one we were talking about earlier. When will a trapezoid, that was the one we looked at. When will a trapezoid be over? Wasn't that the example we just did? Isn't it when it's concave up? Now, does it matter if it's increasing or not? Right? It doesn't matter if it's increasing or decreasing, it matters if it's concave up. In other words, a trapezoid, the top edge of the trapezoid is a straight line. If the curve curves under it, then the trapezoid will be too much. It's going to be old, right? So it's the curvature that determines that. So, concave up, a trapezoid is going to be too much area. And vice versa, concave down, trapezoid's not going to be enough area. It's going to curve over the top of the trapezoid. So concave down, trapezoid will be an under approximation. Now, we've hinted at midpoints being opposite of that. Not hinted, I basically told you that's what it would be. But why? I want you to look at this right here. See if this convinces you. I've got myself a midpoint rectangle right here. Okay? Got myself a midpoint rectangle. Now, is it over or is it under? A little bit of both, right? I mean, this right here, the rectangle's too much area. Right here, we're missing something. So it's a little bit of both, right? So which is it? Well, you could add, well, this curves and this curve, you know, it looks, this piece looks bigger than this, whatever. Okay? But that's not very mathematically, you know, exact to show that. Okay? So we're gonna pull a little geometry out here. Here I've got a rectangle that would be like my midpoint rectangle right here. And it's got a certain area. And this point right here is right in the middle. Now what can you tell me about the blue trapezoid? Why? You're telling me these two cancel each other out. Now give me a reason why those two cancel each other out that your geometry teacher would be proud of and second block couldn't do. I'm here bisect, angles. Natalie, go ahead. Bisect a segment. So this segment is the same as that. What are you talking about? What angle? This angle? Okay, so the word bisect, I don't think would be the word we're looking for.
Oh, it's because they're
Oh, because it's angle side angle thing.
Yeah.
Okay, well, we know this is a mid, okay, angle, man, side angle, side, remember all that, side, all that stuff?
Yeah.
Yeah, okay, well, you're ahead of the other class, just barely, though. It's not looking too good here, but this is a midpoint, so this would be true, right? To mark those two sides as equal, right? We know that. What are these two angles called across from each other? Vertical. Not alternate interior. Lee, you were in the ballpark anyway. Vertical. Anybody have Mr. Cool?
Yeah.
Didn't he? The other day he was saying something about kissing angles or something. Two angles kissing.
Yeah.
I had never heard that in my life. You don't remember? That must be a new thing. That must be a new thing. Now, what we're trying to show is that these two triangles are the same. Right? That's what we're trying to show. Right? If this triangle, if this part we cut off here, we add it on here, if those two are the same, then the blue area should be the same as the red area. Right? That's what we're trying to show. Okay? What are we missing?
Right angle.
Right here. This angle is the same as that angle. There's the old angle side angle. Right? The angle side angle of this one is congruent to the corresponding angle side angle of this one. They have to be congruent triangles, meaning their areas have to be the same. Okay? So, and no matter how much I would pull on this and switch it around, if it goes through that midpoint, that's true. We're going to call that the rotated or adjusted trapezoid. So we can, what we're saying here is we can turn a midpoint rectangle by taking that top and pivoting it. We can turn it into a trapezoid. So now let's go back to the other picture. So if I would do that on this picture, if I would take this top side right here and pivot it, and turn it into a trapezoid, what would happen? Wouldn't it be over the curve?
Yes.
Because it'd be tangent right at this point. I think I got this to where, oops, there we go. Isn't that what it would look like? If we took this top side, we pivoted it, we would create this trapezoid right here, which would be tangent to the curve, as opposed to a normal trapezoid, which would be right there, right? So what we have is a concave down curve. A normal trapezoid would go from here to here. It would be under, approximate the area, right? It would be less than the true area. The midpoint, the pivoted, adjusted midpoint, we can tell would be over because of the concavity. And wouldn't it be the reverse if you had a concave up situation? Right? If you have a concave up, it would be the reverse. So, now we feel more comfortable with that. So what we would have here, what we just showed is a midpoint rectangle would actually, oops, I missed it. A midpoint rectangle would actually be this pivoted thing to be over, and on this one, the pivoted one would actually be under. Right? It would be tangent and it'd be under. So, concave down, midpoints will be over, concave up, trapezoids, or excuse me, midpoints will be under. Concave up, midpoints. So it does turn out that trapezoid and midpoints are kind of like partners. If one's an overestimate, one's an underestimate, and then therefore that's why Simpson's rule works so good. Is that since one's over and one's under, we average them, kind of a weighted average. We get even a better approximation. Okay, so you're going to get some questions about, is this one littler than this one? Is L sub n littler than R sub n? Well, that'll have to do with over and under approximations. There'll be a lot of questions that you don't have to do very much, but just think about them and say yes or no, or over or under, true or false, or whatever. Okay? All right, so there'll be some questions where you do this stuff, where you're going to write this out and calculate some things, and then there's going to be some where it's a matter of just kind of over, under, and that. One last piece of notation, and then I'll let you work. They're going to ask you to find this. Well, what is that? Well, what is I? As far as area. Exact area. This I is the exact area. That's the actual integral that you're trying to estimate by your approximation method. What is L sub n?
Left.
But it's the key word, the last word, approximate. A left is an approximation to the error. So this is approximate error. So what do you get when you subtract those two? the amount of error, right? How much it's off. If you've got your exact area minus your approximation, then that's so this whole thing here is just amount of error. Now, why do we have bars around? Yeah, I know, to make it positive, right? Why do we have bars around? Well, you can have, if you have negative error, what's that mean?
You're over.
If you have negative error, that means that this must have been bigger than this. So all that means is your approximation technique was an overestimate as opposed to an underestimate. So the idea is if I'm asking you for the amount of error, I don't really care if it was too much or too little. I just care how much it was. So the bars are only there to just say, hey, we don't care if it was over or under. If it's positive or negative, we just want to know how much it was. So this is the amount of error, or what they call the computational error. So if the problem says find the computational error, or it says just find bars I minus L3, they want you to find the exact area, just like we did. Find L3, and then subtract them and see how much you were off. That's all that's saying. See how much you were off. Okay, so got a short little chapter here compared to last couple chapters we've done. I'm not really sure what we'll do quiz-wise with this stuff. We won't. We may not. We may throw it onto a later quiz. We'll see. So your assignment is the top line. Okay, 6-1, first line. All right, here we go. Let's get to work, get to work, get to work.
What you got for email is like, either you go about today. Oh, sorry, I just got that. Oh, it is. She doesn't know yet. Unless she email us again. Why would you check on it? It's either be I will get it's already closed up.
If you get hit by the phone,
It is.